Hey guys, welcome back to another video. So here we'll be going through the final part of the series, and I'm talking about questions 12, 13 and 14. Okay, and if you guys haven't previously seen, go through my last three parts and it covers the rest of the earlier questions. And after this part, I'm going to combine them to make a complete walkthrough anyway. But yeah guys, let's go straight to the questions. So 12a. Now they give you a function which is 10e to the minus 0.25x, and you times that against sine x. Now show that the x coordinate of the turning points, so when they say turning points they mean differentiate that, of the curve with equation what we're given satisfies this equation. In other words, you got to differentiate this and somehow rearrange it to get this kind of equation. Now because we got two things multiplied, so let's say we got this term multiply that term, we have to use the product rule, yeah? And this is what we want. We want f prime x to equal 0, or the derivative to equal 0. Because that's how you find turning points. Now, to use the product rule, we need to firstly let something be u and something be v. So I want to go ahead and let the first term be u and the second term be v. Now the product rule formula looks like this, yeah? So now we can say, okay, let u equal the first term and let v equal the second bit. Now if we differentiate the first part, and when you have an exponential, all you got to do is just look at its power and just drop it down, yeah? So it'll be 10 times minus 0.25. That's going to give us minus 2.5. And then we always copy the rest. So this part here never changes, yeah? For v, when you differentiate sine, you just get cos x. And if it was the other way around, if you had cos x, it would become negative sine. So that's how it works. They just flip around each other. Now, because you got everything you need, yeah, you got v times u prime plus u times v prime. All you got to do is just pick v and multiply against u prime first to get the first bit, and then, pick u and then times against v prime. And then put a plus between them, just like I did over here. And because, you're trying to find the turning points, you got to let this equal 0. So when you let it equal 0, you can now move, 2.5, like this first term across, or however you like. But either way, it should look a bit like that, yeah? Okay. Now, one thing we have to note is that we need to get a tan x here. So let's go ahead and just move cos x across by dividing it and then divide this term across. If you do it, you get something like that, yeah? Now, the good thing is, you got the exact same term you're dividing here. So we can go ahead and just cancel these part out right now, yeah? No problem. And in our calculator, we can write 10 over 2.5. That gives us a 4. So that's cool as well. And finally, guys, one final thing to note here is that we want to change sin x over cos x into tan x. Thankfully, that's an identity. These two directly equals tan x. And that's it, guys. We got our answer. And when you get your answer, it's probably better to write the word shown. You never know. I think it's always good to write that. Now, to the next part, yeah? So, figure 3 shows a sketch of part of the curve with equation y equals fx. So, this is what we had previously. So, this is kind of reflecting the first part. This equation right here, yeah? Now, have a look again. B. Sketch the graph of h against t, where this function equals the same function we had here. So if you look back, it's the same function, but now they put this kind of absolute sign. So what I mean, guys, here is that if this original function was fx, so let's just call this function fx, yeah? We now have the same thing, but now they got modulus signs. So what this means, guys, is that when they put these absolute modulus signs, like this means whatever values you had that was negative, it will bounce back to be positive. So you see these values that go below the line, like here, they're currently negative. If you put the absolute sign, instead of dipping below the line, it bounces. So it looks a bit like that. It'll bounce, and then carry on, bounce, and carry on. And I think that's what they want. That's all you got to do. You got to sketch that, showing the long-term behavior. Long-term behavior just means, just keep going to the end, and you're done. Now, let's move on to the part C and D, yeah? So, function ht is used to model the height in meters of a ball above the ground t seconds after it has been kicked. Okay, so literally how high the ball goes, yeah? Using this model, find the maximum height of the ball above the ground between the first and second bounce. Okay, to find the maximum or minimum of any single thing, you always got to use differentiation, yeah? Now, if you look back at part A, yeah, we had this, right? We had tan x equals 4. Now, I'm just going to write tan t, yeah? The reason why is because, we're working with t. I mean, you could write tan x, but it doesn't make a difference. Let's just say, call this tan t. Now, to find the maximum height, let's go ahead and just inverse this and find what t actually is, yeah? So if you tan inverse 4, you're going to get something like this. And so one of the features of tan is that it always shifts 180 degrees. So if you start here, wherever this value is, you know that if you had pi, you're going to get right here again. If you had another pi or 180, you're going to get here again. So what I'm trying to say is, all we need to do, like to find the rest of the solutions, is keep adding pi. Okay, so add as many pi's as you want until it becomes positive. If you add pi to minus 1.326 in your calculator, you should get a time of 1.816 radians. In this case, 1.81 seconds, because that's how we're thinking it. We're thinking of it as if it's in seconds. Now, you're pretty much done, guys, yeah? All you go do now is just substitute this value t into this function here. So let's just write in, replace the t with what you need, and then you get a maximum height of 3.18 meters. And that's it. Now for part D, it says, explain why this model should not be used to predict the time of each bounce. Now it looks to me like it seems to be going in a fixed rate, isn't it? So this is what I said. I said every time, if you bounce a ball, what happens? It always changes, right? It goes slower, slower. Like the bounces kind of reduce. So we say here, why this cannot be used is because the time between each bounce changes. And that's it. So the curve C of equation this, where P and Q are constants, passes through this point and has two vertical asymptotes. Okay, so asymptotes means is that it never ever touches one of the axes, yeah? So it will never reach a certain point. It will just go on forever. With equations x equals 2 and x equals minus 3. Now, explain why you can deduce that q equals 4. Alright, so when they talk like this, all they're trying to say is that we need to firstly look at the bottom, yeah? We're trying to talk about the roots of this equation. That's the thing. So, this is our first thing. We can say this. We can say that the vertical asymptotes, what they're talking about, refers to these two brackets, yeah? And that's when they equal 0. Because the only time you can find a root, or like a solution, if you want, is when they equal 0. So, from the first case, let's just look at x plus 3, yeah? We can say that, okay, from x plus 3 equals 0, we can find x equals minus 3. And that makes sense. That's actually one of the roots. Now, the second case is when you find x equals 2, right? And that has to be from this bracket. We can say also, x equals 2 is found from the second bracket when it equals 0. Now, if you think about, and let's do some writing here. If you replace this x with a 2, so you get 2 times 2, which is 4. You got 4 minus q equals 0. So, essentially, we can see why it's 4 now. So, we can say, therefore, 4 minus q, when it equals 0, will give us what we want. And that's it. That's not much to it. Now, for the second bit, it says, show that p equals 15. Now, this is cool because the reason why they give us a pair of coordinates, and all you can do, guys, is literally substitute these coordinates into this equation. So replace your x's with 3 and your y with a half, and of course replace like wherever you already have. So q equals 4, and if you do that, you're gonna get a massive equation like that. Okay, I like to use brackets personally, like to replace numbers, letters to numbers, because that way you won't make a mistake in your calculator. So if we quickly evaluate this, guys, yeah, we've got 3 times 3, which is 9, so I'll just put this as 9. And then this entire bottom fraction, like you can just put this in your calculator actually, this entire bottom fraction, you should get 12. So that's cool. And now finally, to find p, we just got to clear the fraction. So I would multiply 12 across to get 12 over 2, and oh yeah, and then add 9, and then you're given this. And if you put this in a calculator, well, you can say 12 over 2 is 6, and therefore 6 plus 9 is 15. Yeah, pretty good, isn't it? This question so far isn't so bad. Now, next bit, because there's still a few parts here. And oh yeah, I've updated the function, just to let you know. So, because we said p was 15, I replaced p here with 15, and I update q here with 4. So that's why it looks like this. And I just wrote it here for convenience. So for the next part, it says, figure 4 shows a sketch of part of a curve C. Now, the region R, so this area here, shaded in figure 4, is bounded by the curve C, the x-axis and the line of equation 3. Okay, cool. So here's your line of equation 3, your x-axis, and it cuts at some limit here. So let's just call this one like a u or something, like some upper limit. Okay, show that the exact value of the area of R is a ln 2 and b ln 3, where a and b are rational constants to be found. Okay, so rational constants probably means fractions or stuff like that, not necessarily whole numbers. Now, just a quick reminder, we call this upper limit u, yeah, because yeah, sometimes it doesn't go through. Now, let's do it. So to find the exact area, we're always going to use that integral equation, yeah? Which is always what? The integral from a lower limit and an upper limit. In this case, the lower limit would be 3, and the upper limit we're trying to find. And then we just use the equation we have. So instead of y, it'll be this whole thing in there. So in order to find the value of u, we can see that this curve crosses the x-axis at that point, yeah? So what we can say is, okay, let's use the curve equation and make it equal to 0. Because when you cross the x-axis, we know the y coordinate is at 0. So we can say let y equals 0. So replace that part with 0. And now to find x, well, we should always try and clear the fraction, yeah? The good thing is, if we multiply all of this thing across, so 2x minus 4 and x plus 3 across, you can have 0 times that. Well, 0 times anything is 0, so you're just left with that. And this is easy. You just move 3x across, divided by 3, and you're going to get a 5. Perfect. So updating what we got, we have this. So we can say that the region is going to equal this integral. Yeah, and to do it nicely, I think the best thing we should do is try and factorize some numbers, yeah? So it always helps to break it down. So you see the 15 minus 3x, let's just put it here for a second. We can actually factorize the 3 out of this. So we're going to have something like 3 times 5 minus x, yeah? And on the bottom half, well, we got 2x minus 4. If you factorize 2x minus 4, so let's write 2x minus 4, you can take a 2 out. So it's going to be 2 bracket x minus 2. And the point of this, guys, is you want to take out 3 and 2 outside integral. And trust me, guys, this will make the final answer easier. So it'll look a bit like that. 3 and 2 is outside this. Now, the next step is to literally separate this into 2 separate fractions, yeah? Because that's the only way to integrate it. When you've got loads of parts like this, like 2 linear terms, you got to use partial fractions, yeah? And for the sake of simplicity, guys, I'm going to stick this 3 over 2 next to the top line, yeah? Because it's the same thing. And the partial fraction says this. You can split this whole thing into one part over x minus 2 and another part b over x plus 3. So now, guys, all we want to do is work out a and b. So let's do it. So what we do next in partial fractions is that we should always clear the fraction, yeah? So we're going to go ahead and multiply x minus 2, x plus 3 across this equation. And when you do that, guys, you're going to notice that these two cancel out and a and b both get the opposite terms. Okay, a bit like that. And now the next step is to actually work out a and b. Okay, and that's what we got to do. Now to work out a or b, all we got to do is just pick 2 values of x, yeah? I'm going to make it easy. I'm going to try and pick a value x, which makes this entire term cancel out. And that is 2. So if you said, alright, let x equals 2, you're actually going to get this for the whole equation. You're going to get all this replaced by 2, so you can get 3 over 2 times 5 minus 2, a times 2 plus 3, and then b times 2 minus 2. Well, clearly this part is going to be 0, yeah? Because that's what we want to do. So you're going to have basically 2 parts here. The left side is 9 over 2, and the right side is 5a. And then dividing 5 across, you get 9 over 10. And that's one solution. Now for the next part, we're going to do x equals, we want to eliminate a, yeah? So we can pick another value. Let's pick, I don't know, x equals minus 3, because that cancels out. And if you do that, well, plug in minus 3 across, you get something like that. And you'll notice again, just like the first case, this reduces to 0, because I think that's what we want to do. And on the left side and the right side, they reduce to something like that. That's just 12, that's just minus 5. And again, dividing minus 5 across, and you get a b value of this. And that's it, guys. So you got 2 values. And now what we can do, we can update our integral, yeah? So let's remember, we can just replace our a and b, so we're going to actually use this 2 here, yeah? So always remember, we're using this from now on, yeah? Replacing a and b what we got. So here's our original integral. It now equals that. Perfect, yeah? So now we can actually integrate both of these. So the rule to integrate this is that when you integrate, you just get a log. That's it. When you get a fraction, you get a log. So naturally, you're going to get 9 over 10 ln that plus, or in this case, minus 12 fifths ln x plus 3. And we've got limits here, so we're going to integrate from 3 to 5. In other words, you're going to firstly plug in 5 for x, wherever that is, take away, plug in 3. We're going to keep this in exact form because the question said give your answer in the ln form, yeah? So replacing x with 5 first, you're going to have 5 take away 2, which is 3, 5 plus 3, which is 8, so that checks out. And then minus, and I use a curly bracket. You can use a circle, like the regular curved brackets. And then replacing x with 3, you get ln 1, and you're going to get ln 6. That's it. So let's take this on the first page again. Now, the nice thing about this property, guys, yeah, is that this entire part ln1, well, ln1 is actually 0 in your calculator. This will give you a 0. Okay, so that actually crosses out. So what you're going to actually have now is just this, yeah? It simplifies nicely. So what we could do is just expand the bracket. You got double minus, makes it a plus. And yeah, we're almost there. If you remember correctly, guys, yeah, the question said that we need to find the exact area of this in terms of ln2 and ln3. Well, so far, this part is cool, yeah? We got that. However, these two are not in the right form. Now, we kind of have to change the right form. The good thing is, guys, yeah, we can use the calculator to check out ln8, which simplifies, but the calculator does not simplify ln6 properly. So what do? We take each of them here. So let's take the first one. So I did over here. So the good thing is you can just write ln A in your calculator and you're going to actually get 3 ln 2, which is nice. And then, well, 12 fifths times 3 is just 36 fifths. So you're going to have minus 36 over 5. And that's cool. That's literally one of them done. So you got another term ln 2. Now let's take out ln 6 here. Let's focus on this one for a second. Now, you can't do the same trick because I've tried it and you still get ln 6. What you have to do instead is to realize that there's some kind of rule here. Now, if you remember, if we like multiply two ln's here, so let's say, I don't know, sorry, if you add up two ln's, like ln A plus ln B, we actually get ln A times B. Now, we have to kind of work backwards, yeah? So we can kind of see that ln 6 is the same as saying 2 times 3, or in this case, ln 2 plus ln 3, okay? And well, if we expand the bracket, you're going to have 12 fifths distributed to both of them. So that's how it looks. So therefore, guys, we can now substitute both these expressions for the first two. So for this one and this one, and now writing it below here, yeah, we should get this. That's it. And all you do is collect like terms, yeah? So in our calculator, I don't know, we can say 9 over 10 plus 12 fifths and minus 36 over 5 and 12 fifths. So do them separately, you should get two terms. Minus 24 over 5 for ln 2 plus 33 over 10 for ln 3. And that's it, guys. We've done the question. In the mark scheme, however, they'll give you a decimal form. So they'll write this as 3.3 and minus 4.8. So both is fine, guys. Both is fine. So we have a curve C in the standard Cartesian plane and is defined by the following equation. Okay, so notice that now x is the subject. It's usually y, yeah? So we need to be careful with that. It says that the curve C passes through the origin. So we know it passes through the point 0, 0. Find the value of dy over dx at the origin. Okay, so this is dy over dx. We can't do dy dx. We can only do dx over dy. Yeah, so that's what we want to do. Now, to differentiate this one, it's just the same rules. You literally differentiate sine. We know sine becomes cos. And because you got 2y, it will become, instead of 4 sine 2y, it becomes 8 cos 2y. So you always differentiate 2 and you multiply against the 4. 4 times 2 is 8. And now it says find the value of this at the origin. So you just replace y with 0, and you're going to get something like that. You say at the origin, we have this. Cos 0 is 1, so 8 times 1 is 8. Therefore, that's dx over dy. Therefore, dy over dx is the reciprocal. It's 1 over. So it'll be 1 over 8. And you got it, guys. This is literally all you got to do. Now, for part B, it says use the small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. Okay, let's be clear here. For the small angle approximation, when you're dealing with sine, so let's say sine theta for a second here, this is approximately equal to itself, theta, for very small values of x, for small values of theta, sorry. What that means is that theta has to be like, I don't know, 0, 0.1, so basically close to 0, very close to 0. It can't be 1. Sine 1 doesn't equal 1. Sine 1 equals something else, okay? Now, for part 2, it says explain the relationship between, oh wait, we haven't even done it yet. Use a small angle approximation for sine 2y to find an equation linking x and y. Okay, so let's do the same thing. If sine theta is approximately theta, that means sine 2y is approximately 2y. So we could actually replace this sine 2y with 2y from the beginning. So we're going to say, okay, that means x is approximately 4 times 2y. So therefore, we can say that x is approximately 8y. And part 2, explain the relationship between the answers to A and BI. Okay, so let's just have a look a second. For part A, we have basically a gradient dy over dx of 1 over 8. Now, if you look at this equation, this is actually the same thing. If you make y the subject, so let's divide A across, you're going to have y, which is approximately 1 over 8. So in fact, all it is that they both have a gradient of 1 over 8. And that's your answer. So you can say the value of 1 over 8 is the gradient in both parts. That's it. That's, I think, all you should say. And now let's move on to the final part of the question, which is part C. So let's do this, and then we can wrap up. So show that for all points in the x and y coordinate lying on C, we can get this gradient equation, dy over dx, where a and b are constants to be found. Now, the problem with this question, guys, is that there is no actual build-up to this. Yeah, we don't really know where we're going. But in fact, we have some information, you know. We're given an x value of this from the previous question, and we found out that dx over dy was this. Now, but they want dy over dx, not dx over dy. So immediately, we need to flip this upside down. So it's going to be 1 over 8 cos 2y, which equals dy over dx. So the next step now is how do we go from cos 2y into this square root function, okay? And there's a nice trick to that. The trick is that we need to use an identity, a trig identity. You can't use the sine x over cos x equals tan identity, so we've got to use the other one, which is the sine squared plus cos squared equals 1. Because our angle is basically 2y's, we're going to replace that usual x or theta with 2y. So this is our identity. So what we can do, we can go ahead and make sine 2y the subject for the first x equation. So if I divide 4 across, we're going to have x over 4 equals sine 2y. Okay, and I'm going to go ahead and substitute this x over 4 into the sine squared expression. So it's going to be x over 4 squared, meaning we're going to have x squared over 16 plus the rest, and copy the rest. Now, what we want to do, we want to try and make cos 2y subject so we can factorize into here, and it will look a bit like that. So minusing this term across and square rooting, you're going to get something like that. So now we can actually substitute this expression into the dy dx to replace cos 2y with that, and it'll look like this. So it'll be 1 over 8 times that. Now, to solve this completely, we have to try and rationalize this here. So we need to kind of get rid of that 16 and just leave it as a nice x squared, and we're done. And the best way to do this, guys, is to times up and down by root 16. So always times it by itself. That's usually the trick, because it's like times it by 1. So for the rest of this, I'll do it manually. Now, if I times the top by root 16, well, we're just going to get root 16 on the top line. On the bottom, however, we can choose to times root 16 by its surd or by the whole number. Well, because we're working in surds, I like to times root 16 with its actual surd. So you times everything inside by 16. So 1 times 16 inside the surd, well, let's write 8 for a second. We're going to have 16 minus, and then x squared over 16 times 16, well, they cancel out. So you're just left with x squared. Cool, and that's cool. Now, and then finally, guys, well, we know that root 16 is actually the same as 4. So essentially, 4 over 8 is 1 over 2. So our final answer is going to be 1 over 2 times the square root of 16 minus x squared. And that's it, guys. That's this question done. I just want to thank you guys for coming to this end of my channel, and if you've enjoyed the content so far, just go into my channel page, hit the subscribe button and hit the bell for more notifications, and if you want, you can do personalize or all, and that way you won't miss any future maths or educational videos. Anyway guys, thank you for watching and see you next time. Ciao.